Okay, that is very important. So in comparison to the descriptive statistics, the inferential statistics is quite complicated, I would say, because we need to make some guess about the population using our sample data. But it is also very important because most of the time we are interested only in the population data rather than the sample data. Now, because it is so complicated, if you go to the page for the inferential statistics, you actually find that I have two versions of the lecture notes here. Okay, if you are with your computer, you can go to this website, look at the inferential statistics page, and then you can find two versions of the lecture notes for this topic. 3 years ago, when I first taught this topic in the SPSS class, I was using the full version. The full version is a little bit more detailed, but later I found that the students found it too challenging to learn in this full version of the lecture notes. So that's why later I developed a simplified version of the lecture notes. So in today's class, I am going to use the simplified version of the lecture notes, but if you need more help or you need more details, you can refer to the full version later. Okay, so that is the what I'm going to do today. So let's look at the outline for the lesson for today. First of all, I will spend about 1/3 or at most half of the time today to talk about the concepts of inferential statistics. So there are multiple concepts that are involved in the inferential statistics. The confidence intervals is one of them, but most of the time you will be dealing with what we call the hypothesis testing. So that I will spend most of today's lecture time on this topic here, hypothesis testing. And this kind of hypothesis testing can be done on different types of data. For scale data or numerical data, we can do hypothesis testing. You might have heard about, say, the one sample t-test. You might have heard about ANOVA. So these are the types of hypothesis tests that we can do on the scale or numerical data. But you also know that sometimes we have other types of data, such as the categorical data, which includes the nominal data and the ordinal data. So for these types of data, we cannot use the t-test or the ANOVA. Instead, we have other types of tests, such as the chi-square test, and also we have non-parametric tests. So these tests are also very important. So when you do your data analysis, it is important that you know how to pick the correct test to use. Because, for example, if you are dealing with ordinal data, but you are using the t-test or ANOVA to analyze your data, then that will be a wrong thing to do. And the results that you get from the test will not be meaningful at all, or at least they will not be reliable or valid. So that is the difficulty that you have to deal with when you do the hypothesis testing. But in today's lecture and also in the demonstration, I will show you how to pick the correct test to use in your hypothesis testing. So I hope that will make things a little bit easier for you when you actually come to analyze your own data. So finally, in the second part of today's class, I will do some demonstration in SPSS to show you how we do all these inferential statistics on the computer. All right, so that is what we are going to do. Now, I want you now to click on the simplified version of the lecture notes, and let's look at the lecture notes together. Okay, this is the lecture notes. So first of all, let's talk about the concept of the inferential statistics. Now, as I told you, inferential statistics, this name comes from the word infer. Infer means that you want to make a guess about the population. And in this case, we are doing it by using the sample data. Now, in contrast, for the descriptive statistics, we only analyze the sample data and draw conclusions about the sample data only. Now, one problem we face when we do the inferential statistics is that inferential statistics in the conclusion will never be accurate. Okay, that is one point that I emphasized 3 weeks ago in our first class. But let me ask you, just in case you forget it already, can you tell me why the inferential statistics is never accurate? Can you give me some suggestions in the chat room? Why is the inferential statistics never accurate? Why is it always some error in the inferential statistics? Any ideas? Because we always ignore some population. Great. Okay, I have to give you a like here. Now, from my first chapter, okay, let me open that lecture notes again. Okay, 3 weeks ago, we talked about the ducks, if you remember. So when you try to collect some sample from the population, like you try to pick 5 ducks out of the 20 ducks. The 20 ducks here together, they form the population of our study. But the 5 ducks here, they form the sample of our study. So when we pick the 5 ducks here, it means that we are ignoring all the other 15 ducks in our population. But yet we try to draw some conclusions about all the 20 ducks by using the data from these 5 ducks only. So in this sense, you are losing a lot of information about the population. So in our example here, I show you that basically you have 2 answers. If you count all the 20 ducks in the population, you get the answer. You conclude that 1/4 of the ducks were redheads. That is 25%. That is the correct answer because that includes all the ducks in the population. But in reality, we are never able, or we are seldom able to consider every individual in the population. So in that case, we need to consider the sample only. If you consider the sample only here, you are ignoring all the other ducks, and the conclusion here is that 1/5 or 20% of all the ducks here were a redhead. That is what we get from the sample, but we think that the same is true for the population. But of course, this is not the correct answer. And this is not the correct answer because we are ignoring the other 15 ducks in our statistics. But this kind of error cannot be avoided if you need to do the sampling instead of looking at the population. So that's the problem. Yeah, because it measures we try to measure the population, but we are using the sample data to do that, to be more precise. Okay, so this is a problem that we need to face. And the way to face or to tackle this problem, we can never eliminate this kind of errors completely. But what we try to do is to estimate how accurate it is. Okay, it doesn't matter that the answer is inaccurate, but we try to estimate the accuracy or how far it is from the true answer. This is the main idea of the inferential statistics. We know there is error, but we want to know how far our answer is from the true answer. But you may find that, wow, this doesn't look very possible, because if we do not know the true answer, then how can we estimate how far we are from the true answer, right? Now, to understand that concept, let's look at the example here. Okay, let's say we have a population and we want to estimate the mean of a variable in the population. So that is the population mean. We want to estimate the population mean. But of course, again, we only have the sample data, so we need to make a guess. Now, let's say we collect the sample, and from the sample, we find that the mean of the sample is 10. Okay, that is totally from the sample, but not the population. Then we ask the following question. Can we conclude that the population mean is equal to 10 as well? Now think about this. We look at the sample, we find that the sample mean is 10. The sample may be a small one or maybe a large one, we don't know. And then if the sample mean is 10, can we conclude that the population mean is 10 as well? Now notice that the answer to this question is either yes or no. This is a yes-no question. So we are basically saying that, okay, I think the population mean is equal to 10. Is that true? Or is it likely that it is true based on our sample data? Okay, that is the idea behind this question. Now you may further ask, why do we think that the population mean is 10? Now remember that in our first class, we say that the quantitative method is more confirmatory. Confirmatory means that you already have some idea in your mind, but you want to try to prove this idea, or you try to confirm this idea using your data. So that is what we call confirmatory. Okay, we already have some idea. Where does the idea come from? Maybe it is from previous studies, or maybe it is some kind of requirement, like we want the population mean to be equal to 10. But of course, in reality, it might or might not be equal to 10. So we want to see, or we want to test if this is the case. Okay, so that's why we have some number in our mind that we want to confirm that the data support that number. So that we are asking a yes/no question here. Okay, so look at this again. Now, if we want to know if the population mean is equal to 10, but the sample mean we find is already equal to 10, then it seems quite reasonable for us to conclude that the population mean is really equal to 10. Okay, that is quite straightforward. But you know, when you collect the sample, of course, sampling itself will lead to error. Like if you look at the ducks again, okay, I select these 5 ducks by random. Okay, so I get the answer of 1/5 or 20%. But suppose that another person is also doing the sampling, but he or she just select other 5 other ducks in the sample, like select this duck, and then these 4 ducks here. So the answer in the sample will be different, right? Every time you select a sample, you might be selecting something different. And so the sample mean will also be different. So suppose that in another occasion, someone is still trying to conclude if the population mean is equal to 10 as well, but that person might be he or she is a little bit unlucky. The sample mean in this case is 10.2. That is not exactly equal to 10, but still quite close to 10. So the question is, if the sample mean is 10.2, can we conclude that the population mean is 10? Okay, that is the question that we want to ask in this case. Okay, and then in this case, people may think, wow, 10.2, of course, it is not the same as 10, but this number is not too far from the 10. So people may think, well, okay, there is only a 0.2 difference here. So maybe this difference is due to random error, and the population mean is still equal to 10. Okay, so this is how some people might consider in this case. Okay, but what if we consider another case? This time we draw the sample and the sample mean is equal to 10.5. Now, obviously 10.5 is further away from the 10 than the 10.2, right? So there is a larger difference. Now, is this difference still a random error, or is it really some indication that the population mean might not be equal to 10? Okay, so to determine this, basically we are trying to see, is this number close enough to the number 10 here, to the answer that we want to check. Now 10.2 might be close enough, 10.5 might be further away, but some people might still think that it is close enough. But how about another case? What if we get sample mean of 11? Now, of course, compared with the other two numbers here, the 11 is really quite far away from the number 10. So in this case, we might not believe that the population mean is still equal to 10. So people might might think that another number might be more possible, something closer to 11. So this example shows that when we try to estimate how accurate our answer is, we try to see how far our sample mean is from the number that we want to confirm. If what we want to confirm that the population mean is equal to 10, but the sample mean is really quite far away from the number that we are trying to confirm, then we might not be that confident that the population mean will really be equal to 10. But if the sample mean is actually quite close to the number that we want to confirm, then we might think that, well, this might be a random error. Okay. Now the problem is how close or how far is far enough. It is quite difficult to determine because it seems that we need to set some boundary somewhere in the middle, so that if the number is to the left of that boundary, then we say that the population mean is still equal to 10. But if the number is further away from that, then we might say that the population mean is not equal to 10. So let's say some people might want to set a boundary here, okay, somewhere here. So in this case, if we set a boundary here, then the 10.2 and 10.5, they are to the left of the boundary. And we say that because they are to the left of the boundary, we say that they are close enough to 10. And so we conclude that the population mean is equal to 10. But for the 11 here, it is on the right-hand side of the boundary. Then we conclude that 11 is too far away. And we cannot still believe that the population mean is equal to 10. So setting a boundary is the main idea here. All right. So and then you may wonder, how do we set the boundary? Now that is what I am going to tell you next. Okay, now, but before that, this is the concept that I have told you. When there is some error, when the sample mean is not equal to the expected population mean, then that might be due to random error, or there might be a true deviation from the expected value? We don't know, okay? And we want to find out by the statistical test, all right? So how do we do the statistical test to determine whether the population mean is equal to 10 or not? Now, basically, we have to do a few steps. First, you need to determine the hypothesis. Hypothesis in Cantonese, we call it 假設. Okay, that is something, it means something that you want to test whether it is true or not. Now, but how do we write down the hypothesis? I will tell you the more details in the following pages, but one consideration is how many groups of samples are being tested. Now, what I mean is that, for example, you look at the outline here again. I have a number of different hypothesis tests here, and different hypothesis tests here. Here you see, I write down one sample, okay, and then in another one, I write down two samples. And for this ANOVA, I say more than two population means. Okay, so two and more than two. So it seems that we do it in different ways depending on how many groups of data we have. So this is what I mean by how many groups of samples are being tested. Now later I will give you some examples to make it clear to you. But for the moment, just try to recognize that the hypothesis depends on how many groups of samples are being tested. Now, and then we choose the correct test to do. And for most students, I would say that this is the most difficult step. So there are a number of considerations here. Again, how many groups of samples are being tested? This is very important. And then we also need to consider the level of measurement. Is it ordinal, is it scale, or is it just nominal data? Okay, we need to think about that. So again, it shows you why the level of measurement is an important concept in data analysis. Because if the level of measurement is wrong, then you might pick the wrong test to test your data, and that is not good. We also need to consider if the data is normally distributed. And finally, we also need to consider the sample size. So that is why people think that this is so difficult. Now, in the simplified version of the lecture notes, I will only give you one example to show you the idea. And then in the demonstration, not future course, but in the demonstration, I will give you more ideas. So let's look at the hypothesis testing. Now, there are 5 steps in the hypothesis testing. First of all, you need to write down the statistical hypothesis. And then you are based on the statistical hypothesis and the level of measurement of the data, you choose the statistical test. That is step 2 and most difficult step. Step 3 is to conduct the statistical test. Now, I used to teach statistics for many years. And when I teach statistics, the students usually find the statistical test extremely difficult. But the good news for you here is that you are not learning statistics here. You are learning data analysis. So the approach will be different, because in data analysis, we do not really care about the calculation involved in the statistical test. Instead, what you need to learn is how to pick the correct procedure from SPSS, how to set the parameters, and then how to click OK to conduct the test. So this step for you, it is the easiest step in the data analysis. You just let the computer do everything for you. You just have to click the button to do that. Now, step 4 is to determine whether the null hypothesis should be rejected or not. Now, this thing looks quite scary for you, but basically it means that based on the output of the computer software, you try to answer the yes/no question. The yes/no question put in here. Okay, that is what I mean in step 4. Okay, and I will tell you what it means by null hypothesis in the following pages. And finally, now this one is quite important. Now, many people in the past, when they use the computer software and they finally got the answer from the SPSS, they think that, well, this is the end of their analysis. But in fact, that is not. The most important thing here is that after you get the answer to the yes/no question to your hypothesis test, you need to write down the conclusion. And the conclusion is not only about the yes or the no. The conclusion is what it means to your research, or what it means to the answers to your research questions. Because we are not doing statistics for the sake of statistics. Here we are doing the statistics because we want to answer the research questions. So once you get the answer, the yes/no from the hypothesis test, you need to write down your conclusion to tell the readers what it means to your research context. Right? This is not a mathematical problem. This is a research problem. So very important thing here. Okay, now let's go through these steps one by one. Now, first of all, let's talk about the statistical hypothesis. Now, for the statistical hypothesis, actually, we have two parts. The first part is called the null hypothesis. Null means nothing. Null means nothing, or symbolically, we can write it as H, and then we have a 0 in the subscript. So we call it H0. The null hypothesis means that nothing new is happening. So, and it represents the assumed or the default situation. So let's say in my example here, we try to see if the population mean is equal to 10. This is the question that we are asking. And in that case, the 10 here is the default value or the expected value. So the null hypothesis in this case will be that the population mean is equal to 10. It means nothing new. This is just following what I have expected or following the default value from the past. Now, on the other hand, we have the alternative hypothesis. Alternative hypothesis means that it is not the null hypothesis. It means that something new is happening. So if the null hypothesis is that the population mean is equal to 10, then the alternative hypothesis is that the population mean is not equal to 10. So just equal or not equal. Okay, so two hypotheses, that is what you need to write down in your case. Now, but when you write down the hypothesis, it is very important that you follow these rules here. The null hypothesis and the alternative hypothesis, now you see that they should be the opposite to each other, the opposite to each other. Now, in a more in a logical language, sorry, in the language of the logic, I would say that the null hypothesis and the alternative hypothesis, they are mutually exclusive. Mutually exclusive means that there is no overlapping here between them. Okay, so it means that if the population mean is equal to 10, then it cannot be unequal to 10. These two cannot happen or cannot be true at the same time. That is what I call mutually exclusive, or in other words, there is no overlapping between these two. Okay, that is very important. Now, when you write down your hypothesis, if your hypotheses are overlapping, then your conclusion will be meaningless. So that is very important. Now, another consideration is that the null hypothesis and the alternative hypothesis together, these two together, they should be collectively exhaustive. So what it means is that they have to include all the possibilities. So it means that when you test your hypothesis, you are asking a yes/no question. So the answer is either yes or no. The yes and no cannot overlap with each other. And also, the yes and no together, they already cover all the possibilities. It is either yes or no. There is no other possibilities. So in this case, the population mean is either equal to 10 or it is unequal to 10. So these two cases together, they cover all the possibilities. So that is the collectively exhaustive. Now, so this is the logic of the hypothesis testing. And in hypothesis testing, we always assume that the null hypothesis is true in the beginning, and then we try to see if there is any evidence to reject the null hypothesis. Okay, so it means that in the beginning, we assume that the population mean is equal to 10, and then we try to see if there is any evidence to reject this null hypothesis using our data. Okay, so in our case, let's look at it more closely. Now we want to ask the yes/no question that whether the population mean is equal to 10 or not, and then we write the null hypothesis is that the population mean is equal to 10, and the alternative hypothesis is that the population mean is not equal to 10. And of course, you can also use the symbol to present this. The symbol for the population mean is the Greek alphabet mu. And so you can mathematically, you can say that mu is equal to 10 or mu is not equal to 10. And these two hypotheses are mutually exclusive because they do not overlap with each other. And they are also collectively exhaustive because these two cases together represent all the possible cases. Okay, so that is step one. Now, and then the most difficult step, the step two. So how do we know if we want to reject the null hypothesis? Now, what we do here is that we need to know the relationship between the sample and the population. This relationship is what we write here. Basically, you want to know if the sample mean is close enough to the number that we are trying to confirm in the population mean. And in this case, I'm talking about the number 10 here. So we want to know if it is close enough. Okay. Now, but usually, now this is where what is the most important thing. In the numerical data, if the selection process is random, I mean the sample is random enough, then the distribution of the sample data, usually it should follow a distribution like this. This is what we call a normal distribution. So it means that there is some mean here. And of course, some number are different from the mean. But when you are further away from the mean, the probability is smaller, okay? And you are very far away from the mean, the probability is very small. But overall, we assume that the distribution is symmetric. It means that about 50% of all the data are on the right-hand side of the mean, and another 50% are on the left-hand side of the mean, and the shape will look like this. Now, this is what we call the normal distribution. And if this is true, then we can pick a test that is called the t-test. Now, notice I'm saying that if this is true, I mean, first of all, consider that we are using numerical data or scale level data. That is the first assumption here. And second, we are assuming that the sample mean will follow the normal distribution. Okay, if both of these are true, then we will use the t-test. Now, I will tell you about the other cases later in the demonstration, but for now, let's just focus on this simple example. Now, if this is true, then we do the t-test. So step 3 here, we conduct the test. Now, in SPSS, it means that, first of all, you need to prepare the data. I mean, you need to import your data into SPSS and then clean the data. You did that 3 weeks ago in our first class. Okay, prepare the data. And then you choose the test from the pull-down menu of the SPSS. You set the options, and then you just let SPSS do the work. That is step number 3. Step number 4. Now, after I run the SPSS procedure, how do I know the answer to the hypothesis test? Now, it turns out that the answer is not that straightforward. When you look at the SPSS result, you will find a number. Now, this is the most important number that you need to read in the SPSS output. Okay, I will show you the output here, but for now, let's just look at this page. The SPSS will give us a p-value as the answer. Of course, along with many other numbers, but the p-value is the most important one. The p-value is the probability that we will make a mistake if we reject the null hypothesis. Now, what does it mean in here? Now, first of all, how does SPSS calculate the p-value? Basically, it is based on the assumption that, first of all, the data here are scale level, and second, the sample mean follow the normal distribution so that it knows that the further away from the center, the smaller the probability. Now, this is the assumption behind the t-test. And this assumption is also used when SPSS calculates the p-value for the t-test. Now, I will skip the mathematics of the calculation here, but just to let you know that this p-value comes from the normal distribution assumption. And if it is not normally distributed, then we have to find another way to do it. Okay, now the p-value is a probability. The probability that we will make a mistake if we reject the null hypothesis. So let's say if I know that the null hypothesis is that the population mean is equal to 10, but then if we find that we want to reject it, means that we want to say, well, this hypothesis is not true. The other hypothesis is true. Now, when we do this, of course, we are not 100% sure about our answer because in the inferential statistics, we always have error in our sample, right? That is what I have emphasized many times. So there is a probability that if I say that the population mean is not equal to 10, then I might be making a mistake. Okay, there is such a probability. Now, but look at this example in the beginning again. Now, if I say that the sample mean is 10.2, and then if I say that the population mean is not equal to 10, of course, I might be making a mistake. And if the sample mean is equal to 11, and I say that the population mean is not equal to 10, of course, again, that I might be making a mistake. I don't know. But you also know that if I am very far away from number 10 here, then the probability of making a mistake seems to be smaller because really the sample mean is quite far away from the population mean, so from the number 10. So I don't think I am very likely to make a mistake if I say that the population mean is not equal to 10. But if the sample mean is only 10.2, which is very close from the number 10 here, then if I say that the population mean is not equal to 10, then I think that I might be more likely to be saying something wrong, or the probability of making a mistake is larger in this case. Okay, so that's why we need to consider how large the p-value is. We want this p-value to be as small as possible if we want to reject the null hypothesis. Of course, when we want to do something, and I tell you that there is a probability that you are wrong when you do this, of course, I want this probability to be as small as possible. If there is a very large probability that I might be making a mistake, then I probably do not want to do it. Okay. If it is not small enough, then we do not reject the null hypothesis. Now, and then we come to this question again, how small is small? Just like in here, we ask how close is close. So it turns out that people do not directly draw some lines here, but instead they consider how small the p is. And then people usually use one number that is 0.05 as the acceptable threshold. So it means that if the p-value is smaller than 0.05, then we reject the null hypothesis. Because in this case, the probability that we are wrong will be less than 5%. So 5% is some acceptable value in this case. We accept that we might be making a mistake, but it's okay if the probability of making this mistake is smaller than 5%. We cannot completely eliminate the probability of making a mistake, but as far as it is smaller than 5%, then we say, well, it is okay. We want to do this. But if the p-value is very large, like if the p-value is like 90%, it means that if we try to reject the null hypothesis, then the probability that we will be wrong is 90%. So in that case, we probably do not want to do it if something will be wrong 90% of the time. Okay, that is the principle behind the p-value. So if you come to here, it means that people draw some boundary here so that the probability of making a mistake will be less than 5%. Okay, that is how we draw the boundary. So in short, this is how we make the decision. First of all, we check the p-value from the SPSS, and then we look at it. Is p smaller than 0.05? If yes, then we reject the null hypothesis. Otherwise, we keep the null hypothesis, or it means that we do not reject the null hypothesis. Now, remember that the null hypothesis and the alternative hypothesis, they represent the yes-no answers to your yes-no question. So by rejecting or not rejecting the hypothesis, it means that you are answering this yes-no question. And you do this using the p-value. So the p-value really is the answer to your yes-no question. Okay, now this process is a little bit complicated, but as far as you do it multiple times, you will be more familiar with it. And I will be doing this with you together today. Okay, so finally, so based on our decision, we write down the conclusion. So in our case, if we have rejected the null hypothesis, then we say that the alternative hypothesis is true. Or in other words, we say that the population mean is not equal to 10. And then you also want to write down what it means to your research question. On the other hand, if we do not reject the null hypothesis, then we say that the null hypothesis is true. Or in other words, we say that the population mean is equal to 10. And then you write down what it means to your research question. So that is how you write the conclusion. Now let's look at something real. So if you just go to SPSS and you run the t-test in this case, then what exactly you are going to get? Okay, I will show you a demonstration again, but now let's just look at the output. Now, when you do this t-test, we call it a one sample t-test. I will tell you what is not one sample t-test in the demonstration, but for now, we are looking at the one sample t-test. Now, in this output, SPSS actually give you two tables. The first table here is the descriptive statistics. So this part has nothing to do with hypothesis testing. It tells you the sample size here, the sample mean here, the sample standard deviation, and also the standard error mean, which is basically the standard deviation divided by the square root of the sample size. So all of these are descriptive statistics. It is just trying to tell you what the sample is about. Now, and then the result of the one sample t-test is given by the second table. Now, in this case, the first number I want you to check is the test value here. The test value is the number that you are trying to confirm in your data. So the test value here is what you put in the hypothesis here. Now, in this example, we are testing if the population mean is equal to 0 or it is not equal to 0. So notice that we are talking about the 0 here. This is the number that we want to confirm. So we put a 0 here. But in our previous example, we were trying to see if the population mean is equal to 10 or not. Now, in that case, the test value need to be number 10 here instead of 0. So it is very important that when you do the t-test, you always check the test value here to make sure that you are doing the correct thing. If you want to test for the number 10, but you put a 0 here, then you are not testing what you want to test. Okay, very important here. Now, one thing I do not like about SPSS is that when you do the one sample t-test, the default value, the default test value is 0. It will not ask you, it just put a 0 there. And if you forget to change the 0 to the number that you want, and you run the test, and you do not know that you have to check the test value, then the conclusion will be wrong. So this is a very important point for you to remember. Okay, always check the test value. Okay, and then down here we have a few other numbers. We have the t value here. For t-test, it will give you a t value. And then you have a df. df stands for degree of freedom. And for the case of t-test, it is just the sample size -1. You don't have to worry about why this is the case, because we are not learning statistics here. Now, for the t value basically is calculated by the sample mean minus the test value, 0 in this case, divided by the sample standard deviation, and then divided by the square root of n, or in other words, this is the standard error mean here. So put everything together, and my students who are learning in my statistics class, they will have to do this by hand. But here in data analysis class, you simply use SPSS, and then it will give you this number. But these two numbers are not very important in this case. What is important is the SIG. SIG stands for significance, but it is just another name for the p-value. So when you look at the output, you basically try to look for the column that says SIG or significance, or in some software, it is simply called it the P or p-value, okay? So you look at this number and you try to determine if it is small enough to reject the null hypothesis. Now, in this case, we get 0.000. Now, in the data analysis, we will never get a zero p-value. Zero p-value means that if you reject the null hypothesis, the probability that you are making a mistake will be equal to 0. Of course, this will never happen because we never have 100% certainty in the inferential statistics. We never have anything like p equals to 0. But here you see 0, 0, 0. That is because the p-value is so small that if you only look at the first 3 digits of the p-value, you do not see any non-zero digit. You might have something like a 0.000000001, but that 1 will not be shown here because that is very far away. Okay, but anyway, for this case, the p-value is equal to 0.000, and obviously, if you compare this number with 0.05, 0.000 is obviously smaller than 0.05, right? So based on this decision, is P smaller than 0.05? Yes, in this case. And then if yes, then we reject the null hypothesis. But we reject the null hypothesis means that we say that the null hypothesis is not true. But the opposite of the null hypothesis must be true in this case, and that is the alternative hypothesis. So our conclusion here, because the P is smaller than 0.05, we reject the null hypothesis. It means that this one is not true, but this one is true. So our answer to the hypothesis test here is that the population mean is not equal to 0. Okay, so in this case, we have completed the whole process of hypothesis testing. Now, but in this case, some of you may ask, why doesn't SPSS simply tell me either yes or no? Why does it give me a number and then I need to determine the conclusion by ourselves? Why doesn't it simply tell me yes or no? But instead it gives me a p-value for me to draw the conclusion. Okay, do you have any idea why this is the case? Why doesn't it just tell me the answer directly? This is a difficult question, but I want you to think about it. Can you make a guess? Obviously, it is not because it wants to make it more difficult for you to do your data analysis. There is a reason behind that. The reason here is that comes back to here. Now, whether you reject the null hypothesis or not depends on the p-value, and you compare the p-value with the 5% acceptable threshold. But the problem, sorry, but the problem is not everyone is using the 5% as the reference. Now, some people may say that, well, I am willing to accept a higher probability of making a mistake. So in that case, some people might be using 0.1 here. 0.1 here means that it is okay if the probability of making a mistake is up to 10%. Some people are willing to accept that. But some other people, they want to set a higher standard. So in that case, they might be using a smaller number as the reference value here. Just like they might be using 0.01 in this case as the reference. 0.01 means that I can only accept 1% error probability, but not more. So it is okay if there is a 1% probability that I am wrong, but I cannot accept or I cannot tolerate anything more than that. Now, in that case, people might be using 0.01 as the reference value. So it turns out that whether you want to reject the null hypothesis or not depends on the reference value that you are using. And SPSS doesn't know which reference value you want to use. So in this case, instead of just telling you the yes or no, SPSS just give you the p-value, and then you determine the yes or no based on your preferred reference value. Okay, that is why people, the software only give you the p-value. Okay. Okay, now on the right of this p-value, you also have the mean difference. The mean difference is the estimated population mean difference from the tested value. Now, in that case, that is 2.72 minus the test value, which happens to be 0 in this case. But here it is giving you 3 decimal places, and that is 2.716. This number is also not very important. Now, but in the beginning, I told you that in the inferential statistics, there are 2 ways for you to do the inferential statistics. So I have just told you how to do the hypothesis testing, and also along with the principle behind it. But sometimes you do not want to ask the yes/no question. Sometimes you want to ask, okay, I don't know what number I want to confirm. I just want to know what the mean value is. Now, in that case, I am not asking a yes/no question. I am just asking what is the population mean. Now, it turns out that it is also okay to ask the question like this, and the answer is given in terms of the confidence interval. So what it means is that you ask me what is the population mean. Okay, I know the sample mean is 2.72, but what is the population mean here? And then the answer is like this. Okay, I say the population mean or mu here. Now, I am not just giving you one single value because we can never be certain about the answer. We are not certain about anything, but I can give you a range of possible values. And in this case, the answer is that the population mean is somewhere between 2.64 and 2.79. Okay, so this value is actually not the population mean value itself, but the population mean minus the test value. But in this case, the test value is 0, so it doesn't matter. So here I'm saying that the population mean is somewhere between 2.64 and 2.79. But not only that, we also have a percentage here. Now, remember that in the inferential statistics, we always have error. It doesn't matter, we know that, but we also want to know how accurate our answer is. Now, for this case here, the way to represent the accuracy is by using this percentage. And here, this range, we say that this range will be correct 95% of the time. And this range is called the 95% confidence interval. So it means that I know the answer might not be correct 100% of the time, but I want to make sure that it is correct 95% of the time. So again, it means that there is only a 5% probability that this answer will be wrong. And then we are happy with that. Okay, that is 95% confidence interval. We are 95% confident about this answer. Now again, this 95% is not the only possible value that you use. Some people want to have higher confidence, like they might be using 99% confidence interval. They want to make sure that the answer is correct 99% of the time. But some people might have a lower requirement. They might be able to accept a lower confidence, like I may say that, well, it is okay as far as the answer is correct 90% of the time. Then in that case, you can do a 90% confidence interval. Now in SPSS, when you do the t-test, there is a menu for you to set the percentage. The default value is 95. So if you don't touch it, then it will be 95%. But if you want other numbers, you can set it there. I will show you in the demonstration. Some people will use even lower percentage, like I have seen something like 80% or 85% confidence interval. So it means that they only require 80% accuracy. But anything lower than that is usually not common or usually not acceptable by most of the researchers. If you are not sure, just use 95% in this case. Okay, so that is the confidence interval. Now, at this point, I have talked about the concepts of inferential statistics. I have talked about confidence intervals very briefly. And I have talked about the inferential statistics. I am using the scale data and the one sample t-test as an example here. But I have not yet talked about the other cases because I will leave that to the demonstration. And also, I will leave the categorical data to the demonstration. Now, before I take a break, I want to make some final remarks here. Now, sometimes we might be dealing with more than one sample. And sometimes the hypothesis of the t-test might not be satisfied. Like, again, the hypothesis is that, the assumption is that the data need to be scale level. It has to be normally distributed. Now, sometimes it is still okay if the data is not normally distributed, if the sample size is large enough. So the rule of thumb here is that the sample size is larger than 30. If the sample size is larger than 30, then it is still okay if the data is not normally distributed. We can still use the t-test. There is some theory behind that, but I will prefer to skip that for here, just for simplicity. Now, but you know, there are always some situations in which neither of these assumptions will be true. Now, in that case, you need to do something else. If it is scale data, but it is not normally distributed and the sample size is not large enough, then you cannot use the t-test. And in that case, we use another type of test called the non-parametric test. Now, this test does not assume the normal distribution of the data. And so it is applicable in this case. If you are dealing with the ordinal data, such as the Likert scale data, then we do not use the t-test because Likert scale data cannot be normally distributed. We will be using the non-parametric test. And finally, if you are doing a nominal data, then you use the chi-square test. Okay, so these are some names that I will cover in my demonstration. Okay, but here you just simply need to know that the t-test is not everything. Many people are familiar with the t-test, but t-test does not solve all the problems. And in some cases, you need other tests. Okay, that is what I want to tell you in the first part of this lesson. Now, before I take a break, let's do a few Kahoot questions. I have 6 questions here. So again, I will be showing this one, and every one of you, if you are with your web browser, please go to Kahoot and then enter the game pin there to join the game. Okay, it's loading. Okay, this is the game pin. Now please go to this website, or you can also use the Kahoot app and then enter this number. We are going to go through a few questions just to refresh your memory and to test your understanding. Okay, let's see how many students we have here. Around 14. Okay, anyone else? Only 3? 4? No more? Anyone is still trying to get into it, please let me know in the chat room. Or otherwise, I will just start right away. Anyone is still trying to get into it? Okay, let's go with the 5 students. Okay, what should be done before conducting statistical tests? What should be the first step or the first steps before you conduct the test? Yeah. So of course you have to write down the hypothesis and then you choose the test before you actually do it in the computer software. Okay, the second one. Okay, to test whether the population mean or mu is equal to 10 or not, the 2 hypotheses should be. How do you write down the null hypothesis and the alternative hypothesis in this case? Yes, the answer is the second one, just equal or unequal. We always put the one with the equal sign in the null hypothesis and the one without the equal sign in the alternative hypothesis. But I also want to talk about the others. Okay, the red one. For the red one, mu is greater than 10 and mu is not is smaller than 10. Now these two do not satisfy the requirements of the hypothesis because these two cases do not include the case that mu is equal to 10. So that one point is left out. And so these two hypotheses, they are not collectively exhaustive. Or in other words, they do not cover all the possible cases because mu equal to 10 is not here. So the red one is not correct. Now for the green one, again, so the green one is basically similar to the red one, except that you swap between the null and alternative hypothesis. And again, they are not collectively exhaustive. The yellow one is not true because in the hypothesis test, we always put the equal sign, the one with the equal sign, in the null hypothesis. So the blue one is the answer. Okay, number 3. Now we have a normally distributed population. Now when it is normally distributed, it also means that it has to be scale level data. So we want to test if this is true. So what test we want to use? Actually, I have only told you one test. Yeah, the one sample t-test. Non-parametric test. Now, of course, we can also use non-parametric test, but we don't need to do it here because the population is normally distributed. So the blue one is not true. Chi-square test is for categorical data. So it means it is for nominal or ordinal data. Two independent sample t-test. Now, this one is still a t-test, but it involves two independent samples. I will tell you what it means in the demonstration, but in this case, we are just talking about one sample. So the red one is the answer. Question number 4. Now we have a small sample of scale data, but it is not normally distributed. So what should we use? Based on what I told you in the final remarks, what should we use here? Yeah, non-parametric test is the correct answer. Remember that in my final remarks here, if it is scale data, but it is not normally distributed. Now, it's okay if the sample size is large enough, but here, if it is not large enough, as I show you here, we have a small sample. This is scale data, but this is not normally distributed. Then we use non-parametric test. So the blue one is the answer. The chi-square test is never used on the scale level data. Chi-square test is for nominal and ordinal data. So we don't use it here. And two dependent sample t-test. No matter how many samples you have, if it is not normal distribution, and if it is a small sample, then we never use the t-test, any type of t-test, because t-test depends on normal distribution. If it is not normal distribution, then t-test will not work. Okay, so the green one is not the answer. But it doesn't matter if you are not yet familiar with all these, because I will show you all these again in the demonstration. Now, to test if the mu is identical across 3 groups of normally distributed population, what do we use? I didn't talk about it in very much detail, but you can try to make a guess here. Now, we are talking about 3 groups of normally distributed population, 3 groups. Oh, good. Okay. Yeah. So we have one sample here. So obviously this is not for 3 groups. we have two samples here. Obviously, this is not for three groups, and also two samples here. The only possible answer here is ANOVA. ANOVA stands for analysis of variance, but it doesn't matter here. What you need to know here is that ANOVA is for 3 or more groups of normally distributed population. Okay, so the last one. If you want to test if two nominal variables are independent, then what do you use? Now notice we are talking about nominal variables. Nominal variables are obviously not scale level, and they cannot be normally distributed. So which one should we use? Yeah, chi-square test. Now remember, nominal variable is not scale level. So look at here again. The t-test, any form of t-test, like the choice here, the red one and the green one, the t-test requires that you have normally distributed scale data. If it is nominal data, then the nominal is not the same as normally distributed. These are two different concepts, and they are not the same word. So nominal variable means it is categorical variable. So you cannot use t-test in this case. ANOVA is also only for for normally distributed data. So ANOVA cannot be used. The only thing you can use here is the chi-square test. Okay, so let's see the result. The mic. Jonah and okay, again, Alice. Okay, congratulations to all of you. Now, okay, we have the runner-up here. So we have let's take a 5 minutes break, and then when we come back, I will show you the demonstration in SPSS. Okay, 5 minutes. Hello, let's move on. If you are back, please raise your hand in Microsoft Teams, and then I will continue and move on. Okay, let's work on SPSS demonstration. So if you are with your web browser, you can go to activity 3.2 here. If you have SPSS at home, you can download this data file. I am using this data file, which is the same one as last time for our demonstration. And you can also open this link. This is the same supplementary information from last time. And inside here, you see the Google document. So last time, we have already gone through the descriptive statistics session in this document. And from there, you know how we do the descriptive statistics in SPSS. Okay, now this time, I want to move further to talk about the inferential statistics here. And in the future, when you are doing your own statistical analysis, you can also refer to this document, because in this document, you see that I have already categorized the different types of hypothesis tests. Like if you are doing a scale level data and you are not, and you are assuming normal distribution, then you can do the test listed here. And I have already put down the detailed steps along with the type of hypothesis in each case and how to interpret your answer. And then if you are doing scale level data, but that is not normally distributed, or if you are doing ordinal data, then in that case, you use the non-parametric test. And I have also put down the procedures here for you to follow. Finally, if you are doing categorical data, then you use the chi-square test. And here is the set of procedures. So everything is given here. Now, what I want to do now is to use my demo data set to go through some of these tests with you together. If you have SPSS, you can do it with me together. Or otherwise, if you don't have SPSS at home, you can simply watch my demonstration. Okay, this is the data set from chapter 2 from last time. So again, to just remind you a little bit, this is our my real research data with 708 records. That means that 708 people respond to my questionnaire. And these are primary school students. We have the gender. If I click on the value label, okay, it actually shows the gender labels here. We have different classes. We have different grades. We have grade 4, grade 5, and grade 6. Okay, 3 different levels. And then 5 questions that are ordinal level. And then we also have 3 other variables that are scale level. Okay. So let's see what we can do here. Now, first of all, we can test the scale level data. And in this case, we have the scale level data here on the right-hand side. So let's just pick one of them to do some tests. Now, there are a number of tests that you can do. The first one that I want to talk about is the one sample t-test. Now, in the menu here, under the Analyze menu, now last time we used the descriptive statistics to do our analysis, but this time you need to move a little bit downward and look at the compare means menu, because as you see in the hypothesis testing of the scale level data, basically we are comparing the mean with other numbers. So we go to the compare means. The first menu here is something called the means. Now, I don't usually use this one because the mean here, basically it tries to compare the means of different groups using descriptive statistics only. So that means it is not doing inferential statistics. So that is not very useful here. So I will usually just skip this one. Now, and let's do the one sample t-test. So for the one sample t-test here, as I told you, you need to set some kind of a test value. Now, to do the one sample t-test, first of all, you write down your hypothesis. Now, according to my example here, okay, let me make it bigger. Okay, or otherwise it might be difficult to read. Okay, so for the one sample t-test, the hypothesis looks like this. The population mean is equal to some test value, like 10 or 0 or something. And the population mean is not equal to some value in the alternative hypothesis. Now notice the symbol. Some people use HA to represent alternative hypothesis, but some other people use H1. They mean the same thing. Okay, so it doesn't matter here. Now, so let's say if I want to test if my value here, X1 here, I want to know if the population mean is equal to some test value. Now, let's say we put a 3 here. So it means that I want to know if the population mean is equal to 3. Okay, so we put a test value of 3 here. And for the variable, now notice that for the t-test, we can only use scale level data. So we cannot put the Q1 to Q5, or we cannot put the grade, the gender, and etc. into the t-test. Now, if you, in your research, if you want to test a number of variables, you can put all of them into this box, just like this. And then SPSS will do the test to each of the variables. So that will save you some time if you want to do a lot of tests like this. But for simplicity here, let me only do one of them. So I only test X1, which is the creative thinking. Oh, by the way, some practical skills. And sometimes if you have a very long label like this, and you do not see the variable in this case. Now, if you want to simplify things a little bit, you can right-click here and choose display variable names rather than display variable labels. And in that case, you will only see the variable name. Of course, sometimes it is more convenient, but sometimes it is not. It depends on how you set up your labels and the variable names. But anyway, now we have set the X1 here, and I have set the test value here. Now notice that the original default value is 0. And it is very important that you remember to change this one to the value that you want. And look at the option here. Now the option here, you can enter the confidence interval percentage. As I told you, some people use other value and some people use smaller value. So 95% is the default value. Okay, so I click OK, continue here. Yeah, we do not change that. And then we click OK. So this is the output. Again, as I show you in the lecture notes, the first table is the descriptive statistics. So we have the sample mean of x1. x1 is creative thinking in this case, and sample mean is 2.9106. We have the standard deviation and the standard error. Now we are testing if this population mean is equal to 3. Okay, we don't know, but we use the sample mean to test this one. So if, as you remember, the idea behind this is we try to determine if the sample mean is close to the test value or not. So is 2.9106, of course, it is not equal to 3, but we want to know if this is close enough to 3 or not. So we do a t-test, all right? Now, here is the result given by SPSS. And first of all, we check the test value, make sure that this is the test value we are trying to test. In the table here, we have the t value. As I told you, it doesn't matter what you have in the t and the degree of freedom here. And the most important number in this case is the SIG, or the p-value. Now the p-value here, it gives you 0.000. So again, we want to know if the p-value is smaller than 0.05, because the p-value gives you the probability of making a mistake if you reject the null hypothesis. Now, the whole process might be a little bit complicated for many of you. So I have put down the tree diagram in this document to help you a little bit. So basically, you look at the p-value and you compare the p-value with a reference value. In this case, it is 0.05, although some people might be using other numbers. And then you ask yourself, is the p-value smaller than 0.05? If it is smaller than that, then we reject the null hypothesis. Or in other words, we take H1 or HA as true, as the answer. We do that because the p-value is the probability of making a mistake if we do that. But the p-value is small enough, so it means that the probability of making a mistake in this case is small. So we reject the null hypothesis. But otherwise, if the p-value is not equal to, or is not smaller than 0.05, then the probability of making a mistake is considered too large. So we do not reject the null hypothesis, or otherwise we take H0 as true. Now, I want you to help me a little bit. Based on what you have here in the diagram, and based on the p-value of 0.000, can you tell me which answer we want to take? Do we reject the H0 or do we not reject the H0? Can you tell me the answer in this case? P-value is 0.000. Reject or not reject? Okay. One of you say we do not reject. Do not reject means that you go to the upper side, right? Any other suggestions? Oh, you mean yes. Okay. Yes means you reject the H0. So look at here. So we ask, is P smaller than 0.05? And obviously it is, because P is equal to 0.000 according to here. Okay, 0.000. So it is smaller than 0.05. So we go to the lower arm, and the conclusion is to reject H0. Reject H0 means that we take H1 as true. So in other words, we say that in this case, the population mean is not equal to 3. That is the answer given by SPSS. And you say that is so confusing. Yes, that is true. I agree with that. So, but the way for you to tackle this thing is to do this a number of times, and then you will find it actually quite straightforward. Now, to help you a little bit, I will do this a number of times and show you what happens if I use a different test value. So in our first test here, we are using the 3 as the test value, and the conclusion as told by SPSS is that no, SPSS does not think that the population mean is equal to 3 because it thinks that it is too far away. So the conclusion is that the population mean is not equal to 3. But what if we use another test value? So let's say the population mean is 2.9106. So what if we test another value which is closer to the sample mean? Now let's say instead of 3, we want to know if the population mean is equal to 2.91. So 2.91 in this case is closer to the sample mean that we get. Now to do that, we go to the one sample t-test again. And this time, we change the test value to 2.91. We do not usually change it like this in our research because once you get the value to test, which is based on previous data or based on theory, you do not just change it to another number. But in this case, I want to show you what happens if the sample mean is closer to the test value. So let's see what we get here. 2.91 in the test value. Now look at the p-value in this case. P-value in this case, it is 0.977. And we are testing the test value of 2.91, which is closer to the sample mean. Now, look at the tree here again. 0.977 is a large number. Now you go to this tree and then you ask, is the p-value smaller than 0.05? Obviously, it is not in this case because p-value is equal to 0.977. So in this case, the answer is we do not reject H0, or otherwise our conclusion is that the population mean is equal to 2.91. Why does it give me a conclusion like that? Because this time the 2.91 is very close to our sample mean. We are closer to that, so we think that might be the difference is just a random error rather than a real difference. Okay, now in other words, what happens if we insist that the other one is true, then you have a probability of making a mistake. And according to the p-value, the probability of making a mistake when you choose the second one as the answer is 97.7%. That means that if you say that the second one is true, then the probability that you are wrong is 97.7%. You are wrong 97.7% of the time. Then of course, I don't want to choose this one. Now, I want to make it even more extreme. What if we use a test value that is 2.9106? That is, it is equal to the sample mean up to 4 decimal places. Now, so it means that these two numbers are very close together. Now, let's see what we get. So I changed the test value from 2.91 to 2.9106. Okay, that is very close to the sample mean. Now, in this case, we click OK here. The p-value in this case is 1.000. Now, again, there is no certainty in inferential statistics. 1.000 doesn't really mean 1.000. It might be something like 0.99999, many nines after that, but you round it up and you get 1.000. So in other words, this is a very large probability. So again, we look at the tree diagram. P is 1.000. Is it smaller than 0.05? Of course it is not. So again, we go to the upper branch and we do not reject H0. Or in other words, we choose the H0 as the answer. The conclusion is that the population mean is equal to 2.9106 because they are really very close together. Now, on the other hand, if we insist that we choose the second one as the answer, then what is the probability of making a mistake here? According to the p-value, because the p-value is 1.000, it means that if you choose, if you choose the second one as the answer, then the probability of making a mistake is 1.000. You know, probability goes from 0 to 1. 1.000 means that you are almost always wrong if you choose the second one as the answer. So that means that we should not choose the second one as the answer. So we choose the first one. Okay, so that is how you do the one sample t-test in SPSS and how you draw the conclusion in this case. Quite complicated, quite confusing. I agree with that. But the only way for you to tackle this is to do this many, many times. And then you will get familiar with it. And the way to do this many, many times is to run this analysis many times and then use the tree diagram here to draw your conclusion. So if you are not sure, just follow the tree diagram. Okay, you can always use this one. Okay, so that is the one sample t-test. Now we do something more interesting. We do the independent samples t-test. Now look at our data again. In our data here, we have X1, but we also have two types of students. We have female students and we have male students. So of course, you can ask if the mean score is equal to some number. That is one way to ask the question. But sometimes we are interested in knowing about the comparison between two groups of people. So in this case, we want to know, now we don't care the score of the female and the male, but we care about if these two groups of people have the same score. Okay, so we want to compare them. Now, the way to write the hypothesis of this type of question is like this. The null hypothesis is that the two groups have the same population mean. I don't care what the mean is. I just care whether they have the same population mean or not. And then the alternative hypothesis is the opposite of the null hypothesis. In this case, it is the two groups have different population mean. So either the same or not the same. We want to know that. Now, there is some complication in this case, but let's do the test first. So to do this test, we go to Analyze, And then again, we compare the means, but this time we have two independent samples. The male and female students, they are two different groups of people. And so we call them independent samples. And there are two of them, so two independent samples. In this case, we use the independent samples t-test. Now, for the independent samples t-test, you do not need to input the test value because we do not care about the value of the population mean. We just want to know about the difference or if there is any difference between the two groups. Now, first of all, I put the variable to be tested on the right-hand side, just like what we have done before. Again, you can put all these variables here and SPSS will do all of them, but for simplicity, let's just use one of them. Now, an important variable here is the grouping variable because you want to tell SPSS how you want to separate, to split the data into two groups. In this case, we want to use the gender variable to split the data. So we put the gender to the right-hand side here into the grouping variable. Now, but notice that if you just do this, you find that the OK button is disabled. You cannot click on it. The reason is that SPSS is a little bit dumb in this case. It is not very smart. Because in the independent samples t-test, you need to tell which two groups you want to use. And SPSS does not know what groups you have in the gender variable. Okay, it doesn't know that they are only male or female. You have to tell SPSS what variables you are using. So the way for you to fix this, you see you have the two question marks here because it doesn't know which two groups to compare. So you click on the Define Groups button. Now in the Define Groups button, you want to write down the values corresponding to the two groups in the gender. Now in my data here, you are looking, you see the female and male, but actually internally, I am using 1 and 2 to represent these two genders. So I put the two numbers here, 1 and 2, so that SPSS knows how to compare between the two groups. Of course, if you are using other numbers, like if you are using 3 or 4, then you put 3 or 4 here. Then I click Continue. Okay, now once you define a group, you see the numbers shown here, and then the OK button is also activated. So you click the OK button, and that is your result. Now this time you get something more complicated. Now, first of all, we look at the first table, which is the descriptive statistics table. For this table, you have creative thinking, but you have data put into two different rows, one for male and the other one for female, because one of them is 1 behind it. In the data, I use 1 to represent the male, and I use 2 to represent the female. So SPSS knows that it wants to put these into 2 rows. We have the sample size for each case. We have the sample mean for each case, and also the deviation and also the standard error. Now, let's just look at the sample mean here. The male here, for the male students, their mean creative thinking score is 2.9125. For the female student, the score is a little bit smaller, 2.9085. So my question is, given these sample statistics, can we conclude that the two groups of students, they actually have the same population mean in the creative thinking? Now, obviously, look at the sample mean. These two numbers are not the same. it looks like the male students are performing a little bit better. But we also know that this is just the sample data, and we don't know if the difference is due to random error or there is really some difference between the two genders. We don't know that. Of course, we know that about the sample, but the sample is not what we are interested in. We want to know about the population. So again, we want to compare these two numbers, do some hypothesis test to determine if these two numbers are close enough for us to conclude that the two genders are the same. So we do the independent samples t-test, and here is the result. Now, this test is a little bit more complicated than the one sample t-test. The reason is that we have two rows here. Now, these two rows has nothing to do with the two genders here. They are two rows for another reason. The two rows here represent two cases. First case is equal variance assumed. It means that the two groups of students have the same population variance. Variance is the friend of standard deviation, the square of standard deviation. And the other case is that they have different population variance. Now, why do we need to do these two different cases? The reason is that for the independent samples t-test, the formula is different in these two cases. You don't have to worry about why the formula is different. You just need to know that there are two different formulas in the two different cases. So before we look at the t-test result, first of all, we want to determine which is the case in our data. Which one should we use? And in order to determine which one we use, we have a Leibniz test for equality of variance. It means that SPSS has already done the test for you, and it tells you which one is true. Now, let's look at this outline here. The Leibniz test for the equality of variance. So if the p-value is small enough, then we reject the null hypothesis. The null hypothesis is that the two groups have equal population variance. Now, in this case, if this is true, then we look at the first row of the t-test result. Otherwise, if this is not true, then we look at the second row of the t-test result. Okay, this is quite complicated, but we just follow the procedures one by one. Okay, now let's look at our result. Okay, we do this one by one. Don't worry. Okay, let me make this window a little bit smaller. Oh. Okay, you look at the magnifier image here. So the first one, now we look at the Leibniz test for equality of variance. The result is given in here. Okay, maybe I need to make it a little bit larger again. Sorry about that. The screen is not large enough to show all this. Okay, now the test for the equality of variance, the p-value is 0.000. So look at this value, and we can use the same tree diagram as before to draw the conclusion. So p is equal to 0.000. Obviously, it is smaller than 0.05. So according to the tree here, H1 is true for the Leibniz test. H1 is true for the Leibniz test. So what is H1 here? H1 here. H1 here is that the two groups have different population variance. So according to this rule here, we want to look at the second row of the t-test result. So let's say what is the second row? Okay, the second row is here. equal variances not assumed. And then we look at the significant value of the t-test. And then the p-value is 0.927. That is the value that you need to read here. We do not read the 0.928 because the Lavani test tells you that you should only read the second row rather than the first row. Okay, so again, the p-value for the t-test is 0.927. And then you look at here again, this tree diagram. 0.927 is it smaller than 0.05? Obviously not. So in this case, we do not reject the null hypothesis. Or in other words, the conclusion in my t-test is that the two groups have the same population mean, the same. Now, what does it mean in my research here? It means that the two genders, although they have different sample mean value, the conclusion is that their population mean value is the same. So it means that if you ask me, okay, do the male and female students perform differently in creative thinking? I will say no. The data shows that they perform the same. They have the same population mean. That is my research conclusion. Okay, the whole thing is quite complicated, so let's go through it once again, but this time a little bit faster. Look at the independent samples t-test. First of all, look at the Lavani's test result. It is smaller than 0.05, so we look at the second row. And the second row gives you a p-value of 0.927. So the conclusion of the t-test is that there is no difference. Okay, now it doesn't matter if you feel feel very confusing at the moment, because when you have your real data, you do this kind of test, you can always follow the steps one by one. It might be quite slow in the beginning, but as far as you follow the steps carefully, you will be able to get the correct conclusion. And if you do it multiple times, you will get familiar with it. And at that time, you don't really need to look at the tree diagram or the hypothesis. Okay, everything will be more straightforward if you are familiar with it. Okay, so here I have talked about the independent samples t-test. The next one. Now this one, the summary independent samples t-test. Now this is the same as the independent samples t-test, except one thing. In the SPSS here, you click Analyze, Compare Means, and then you get, oh, the menu is gone. Okay, so don't worry about it. Okay, in this version, we don't even have that option. Okay, so let's forget that. Now, so we talk about the next one, the paired sample t-test. Now, for the paired sample t-test, we try to compare the pair sample. Now, what do we mean by pair sample? The pair sample here means that now previously we compare between the two genders. So we have male and female, and they are independent groups. So they are independent samples. But what if I want to compare the answers to the two variables for the same student? So let's say I have for each student here, I have the values from x1, x2, x3. So what if I want to know if people's mean score in x1 is the same or different from their mean score in x2? Okay, so we are not comparing two groups of people, but the same group of people over two different variables. Now, in this case, of course, these two variables, they are from the same person. So we say that this is a paired sample. I am not interested in knowing about my X1 score with the X2 score of another person. This is not our interest. We are trying to compare between the X1 score of a particular person with the X2 score of the same person. So in this case, it is called the paired sample. Now, in reality, we usually do it in the following situation. Suppose that you have a pre-test. Pre-test means that in the beginning of the study, you ask them some questions, and then they fill in the questionnaire, and you get a number here. And then you do something to them, like if you can tell them show them some data, or let them go through some video or some training course. So in a hope that they will change their mind, or in a hope that there will be some change in the process. And then at the end of that, you ask them the same question again. Okay, and that will be another variable. So I call it a post-test. Post-test means after that. So, and then I want to compare, is there any change in their view or in their score before and after the intervention? Intervention means what you do to them in the middle. So, okay, is there any change because of the intervention? So you want to compare between the two variables. Now, so let's do it. We go to analyze, compare means, but this time we go to the paired samples t-test. Now, for the paired sample, we do not care about the groups of people, but we want to specify the two variables that we want to compare. So you see that on the right-hand side here, you have variable 1 and variable 2 on the same row. They mean we want to compare these two variables. So I put the X1 on the right-hand side, and then I put the X2 again on the right-hand side, so that both of them are on the same row. Of course, you can compare other variables, but that's not our concern here. So let's just do X1 and X2. And then we click OK. So we have descriptive statistics. We have the two variables here. We have the mean, the sample mean of the two variables. So it looks like the sample mean are not very close together. And then secondly here, we have the correlation between the two variables. Now, correlation is something that tells you how similar the two variables are. If it is close to 1, it means that they are very similar to each other. If it is close to 0, it means that they are not at all related. But this is not our concern here. Our concern is the paired sample test. So again, in here, you see we are comparing between creative thinking and critical thinking. Now, the null hypothesis of the comparison is that the two variables have the same population mean. And the alternative hypothesis is that they have different population mean. So which one is true? Again, there are many numbers here, but we don't care about them. We only look for the SIG. That is the p-value. Now, in this case, the p-value is 0.000. Okay, so very small p-value. Now, again, we use this diagram to draw the conclusion. Now, can you tell me which one is correct in this case? Should we take H0 or H1 in this case? When the p-value is 0.000, very small number. Shall we go to the upper one or the lower one? Yeah, reject H0. See, this is quite complicated, but as you go through it multiple times, when you are familiar with the tree diagram, then things is actually quite straightforward. There is no other way to do it. You just follow the tree and determine if the P is smaller than this number or not. If yes, then you reject H0. If not, then you do not reject the H0. Now, you reject the H0 means that H1 is true. So again, we go back to the hypothesis, which is H1. H1 is that the two variables have different population mean. So here is the answer. You already know from the sample mean that these two sample means seem to be quite far away. But you don't know, you cannot confirm that until you do the hypothesis test. And the hypothesis test tells you this result. The result is that p-value is very small. So according to the tree diagram, the conclusion is that the x1 and x2 in this case, they have different population mean. Or in other words, they are different. Okay, that is the paired samples t-test. Now, so far, we have gone through 3 types of t-test. To summarize a little bit, the first type, you compare the population mean with some test value. Okay, it involves only one sample. That is the one sample t-test. And then we talk about the independent samples t-test, where you want to compare the population mean between 2 independent groups of people, such as male and female. Okay, 2 groups, not more than that, only 2 groups. And then we also talk about the pair sample t-test. Again, you have 2 things to compare, but you are not comparing between 2 groups of people, but instead you are comparing between 2 different variables of the same person. Now, but again, this only involves 2 groups. Now, what if we have 3 groups? When we have 3 groups, or we say we have more than 2 samples, then we need to do something else. The t-test cannot help you. The t-test can only deal with 1 group or 2 groups. But more than that, we need another way. And that way is called the one-way ANOVA. Now, one-way ANOVA is a very complicated thing if you are learning in my statistics class. Let me show you some formula just to scare you. Okay, this is not one-way but two-way ANOVA. But you know, the one-way will be a little bit easier than that. But you look at the formula, it is still very scary. This is the two-way ANOVA. So in my statistics class, I require that my students do all of this by hand. That is statistics, because they are learning statistics. But the good news is that for your case, you don't have to worry about that. You only have to go to SPSS, click on the menu, and get the answer. Okay, this is two-way, and but we are doing one-way here. Okay, so how to do the the one-way ANOVA? First of all, look at the hypothesis. Now, in this case, again, we are comparing the population mean between groups, but this time we have more than 2 groups. So the null hypothesis is that all the groups have the same population mean, all the groups. Now, the alternative hypothesis is the opposite of that, but notice the opposite of H0 is not that all the groups have different population mean. Okay, if they do not have the same population mean, it doesn't mean that all of them should be different from one another. Now, instead, the alternative hypothesis is that at least some of the groups have different population mean. So it means that maybe if you have 3 groups, maybe 2 of the groups have the same population mean, but the third one has a different population mean than the others. Okay, this is also okay. Okay, so that is the alternative hypothesis. Now, in my example here, this time, let's use the grade. The grade here, people can might be from grade 4, grade 5, or grade 6. So there are 3 groups. And we want to know if people from these 3 groups have the same population mean in X1. Okay, so we go to analyze again, compare means. And this way, we go to one-way ANOVA. Okay, by the way, there are also two-way ANOVA if you need to do it, but they are in another menu, so I will skip it here. Now, let's go to the one-way ANOVA. So again, we put the variable that we want to test. In this case, again, we test the X1, which is creative thinking. So we put it onto the right-hand side. Now, similar to the independent samples t-test, we need to specify the grouping variable. But this time, the grouping variable has another name. This is called the factor. I don't know why they don't use the same name, but anyway, might be because different engineers are writing the different procedures. So they are kind of inconsistent with each other, but it doesn't matter. Now, in this case, we put the grade variable into the factor. Now, this time SPSS is smarter. It does not ask you for the labels representing the different groups. Instead, it will determine the different groups automatically. So you just put the grade variable into here. Now, there are other things for you to change, but I will skip them for a moment and come back to one of them later. So we have X1 here. We have the grade here, which specifies the grouping variable, and then we click OK. So this is the result. Now, this time, it only gives you one table. I will go back in a while to show you how to show the other table, but for the moment, let's just look at this one. This is the ANOVA table. It is testing the creative thinking. There are many rows, but fortunately, the only thing you need to look at is this number. Okay, ignore everything else. So the SIG here, again, is the p-value. So we have done this multiple times now. So can you tell me, based on this one, the p-value is 0.000. So can you tell me which one we should take? Yeah, we get H0. Okay, so you start to get familiar with this now. The p-value is quite small. So according to the tree here, is p smaller than 0.05? Yes. So we reject H0. Reject H0 means that we take H1 as true. So in other words, the two variables have different population mean. I'm sorry, not this one. This one, okay. At least some of the groups have different population mean. So we have grade 4, grade 5, and grade 6. And the conclusion is that at least some of them is different. But there is one question that we have not answered. We know at least some of them, or at least one of them, is different. But which one? We do not get the answer from here. We don't know which one. So that conclusion is not very helpful. Now, fortunately, in ANOVA, there is a way for us to get more information from here. Now we go to the one-way ANOVA here again. We go back to here. So we go to the, okay, first of all, we go to the options. The options. Now we go to the options here so that we can choose to display the descriptive statistics of the groups. We did not show the descriptive statistics for ANOVA, so let's show this here. And we click OK, continue. And then we go to the post-hoc test. The post-hoc test, post means after. Post-hoc test is a place for you to further test if any of the group is different from the others. Now, there are many options for you to pick in the post-hoc test. There are actually some criteria to consider, but I will leave that to later when you actually analyze your own data. And for the moment, let's just pick some of them that are most popular. And usually, if you do not have any particular idea, then we usually try to pick the one that is the most popular. Or if you are trying to compare your data with the literature, and the literature is doing this test, then you have to pick the same test. So let's say we pick the Tukey test, okay? Okay, for this case, it also allows you to put down the significance level, and we just use the default value. Click continue here, and then we click OK here. Now this time, for the post-hoc test, you have multiple tables. We can ignore the second one and just look at the first one. Now, in this table here, we are doing a multiple comparison. Now, of course, for the up here, we also have the descriptive statistics. Here, you see the mean value, the sample mean value of the 3 groups of people. So from the number, you already know some of them seem to be further away from the other groups. And then we have the ANOVA table, which is exactly the same one as we got above. Now, the conclusion is that at least one of the group is different. So which one is different? We compare the groups pair by pair. Now, on the first row here, we compare grade 4 and grade 5. And then we look at the p-value. The p-value is 0.013. This number is smaller than 0.05. So the conclusion is that grade 4 and grade 5 are different. Okay, the p-value is small. So we say grade 4 and grade 5 are different. Now, how about grade 4 and grade 6 on the second row? On the second row, we are comparing between 4 and 6. And 4 and 6, the p-value is 0.000. Again, this is quite small. So we conclude that grade 4 and grade 6 are also different. Now, notice that this time, I am not writing down the specific hypothesis because it is already quite straightforward and we skip that part. I do not even need to refer to the tree diagram because that is also quite straightforward after you get familiar with it. So when you are asking if something is the same or not the same, and if the p-value is smaller than 0.05, then they are not the same. Okay, so 4 and 5 are different, 4 and 6 are different. How about 5 and 4? Now 5 and 4, you don't actually need to look at it because 5 and 4 is the same as 4 and 5. So the p-value is the same, 0.13 here, 0.13 here. So 4 and 5, you mean 4 and 5 similar? You mean you look at the sample mean, right? You think they are close enough? Is that what you mean? Okay, 0.013, 0.013. Now, the p-value here is smaller than 0.05, right? So when it is smaller than 0.05, they are different. They have different population mean, just like, yeah, just like here. Every time we do this kind of test, remember I say the equal sign is always in the null hypothesis, and the unequal or anything else is always in the alternative hypothesis. If p-value is smaller than 0.05, it means that, oh, okay, 0.13, no, that is 0.013. Oh, by the way, this is a common mistake. So many people make a mistake when they compare the number with 0.05. So be careful about that. Okay, so 5 and 4, they are the is similar to 4 and 5. So I can ignore that one. And then we look at this one, 5 and 6. 5 and 6, the p-value is 0.147. Okay, are they the same or not in this case? 5 and 6, are they the same or not? They are the same, right? The reason is that the p-value is large. So in this case, we do not reject the null hypothesis. Now, so we get the answer. First of all, from the ANOVA, we know that at least one of the groups is different. But which one is different? We look at here. We say, okay, 4 and 5, they are different. 4 and 6 are different. 5 and 6 are the same. So basically, it's just like grade 4 is different from the other two groups. Okay, so this is our conclusion. Now, the second table also shows you something similar. Now, this table is representing the answer in a slightly different way. Basically, we have 3 groups, and SPSS tries to categorize these 3 groups into different groups here. So 5 and 6, they are together. It means that they have the same population mean, but grade 4 is in its own column. So it means that it has a different population mean. And in this here, you see the numbers. These numbers are the sample mean values. So this table is just another way to represent the same data in the first table. Okay, so the conclusion is grade 4 is different. The other 2 groups are the same. Okay, so that is ANOVA. Now, so enough for the t-test and ANOVA. Now, the next one, we consider some other cases. What if the data are not normally distributed? Or what if the data are ordinal? Ordinal means Likert scale. Many people try to use the t-test to test the Likert scale data, but that is not correct because Likert scale data are ordinal data but not scale data. Now, it turns out that in this case, you need to do another type of test. Oh, by the way, I told you that t-test and ANOVA, they have to follow normal distribution. And there is actually a theory behind that. The theory is called the central limit theory. I don't want to scare you away, so I just put the name here. And if sometime in the future you need to know more about that, you can refer to this theory. Now, for the non-parametric test, in this case, now it turns out that conceptually or theoretically, the non-parametric test is quite difficult to understand. My students in my statistics class, all of them find this extremely difficult to understand. So that is the bad news. The good news is that in SPSS, it is extremely easy to do non-parametric tests. It is even easier than the t-test and the ANOVA. And I will show you why. Now, to do the non-parametric test, again, we have different types of non-parametric tests. And let's go through one of them that is the most popular. So this is the independent samples. Now, it is like the independent samples t-test, except that we do not have normal distribution. So we do not use the t-test. So instead, we use non-parametric test. Now, the way to do it is the following. We go to analyze. This time, we do not compare the means, but we move down a little bit further to go to non-parametric test. So there are 3 options here, along with some legacy dialog. Legacy dialog means it is from a very early version of SPSS. We do not usually use that. Now, instead, let's look at the independent samples. Now, go to this dialog and you see this dialog does not look similar to what we have gone through in the t-test and the ANOVA. The design overall is not the same. And I can tell you the reason. The reason is that this part of SPSS is relatively new. Relatively new. The t-test and the ANOVA, those were written many years ago. And the non-parametric test procedure is relatively new. There is one advantage of that. The advantage is this thing has artificial intelligence. So it is very smart and it can determine something automatically for you. Now, let's go through it together. First of all, the first thing you need to do is to go to the objective. It asks you, what is your objective? It means what you want to do. So most of the time, we just choose the first one, automatically compare distribution across groups. The keyword here is automatically, so that we don't have to worry about how to do it. SPSS will do this for us. Now I will show you what I mean. The second one, now in the fields here, okay, for this time you have no choice, but you have to tell SPSS what variable you want to compare. Okay, even though there is artificial intelligence, it is not so smart that it knows what you want to do. So you have to specify the variables. Now in this case, we want to compare creative thinking. Now again, let's do the same analysis that we have done using independent samples t-test. We put the gender here into the groups so that we can compare the creative thinking across the 2 genders. Now notice that this time you do not have to specify the number 1 and number 2 in the gender. Okay, it is just an example that this procedure is more advanced than the one in the t-test. Okay, specify the variable and the grouping variable, and then we go to the settings. Now for the settings here, you see a lot of grayed out names here. Now these are the names of the non-parametric test. Non-parametric test actually is not one single test. There are many different types of non-parametric tests, and you use different tests in different situations. But the good thing about the procedure in SPSS is that you don't actually need to worry about this because, again, we choose automatically. So SPSS will choose the test based on the data. So we just choose automatically, this one, and then we go to the we go to the run here. Just run the test. Okay, so it might take some time. Now, the result depends on your SPSS version. I am using version 25 here, if I remember correctly. Yes, this is 25. Now, if you are using version 26, you have many more tables following this one. Now, for the result here, first of all, it is a color table, so it is more beautiful. Now, it gives you the null hypothesis. So the null hypothesis here is that the distribution of creative thinking is the same across categories of gender. So basically, it means that it is comparing creative thinking across gender. Now, that is exactly the null hypothesis that we want to use. The alternative hypothesis is not given here, but you know it must be the opposite of this one. So the alternative hypothesis means that the creative thinking is not the same across the gender. Okay, so from here, you already know that this feature is more advanced because it tells you the null hypothesis. And then next one, in the next column, it gives you a very horrible name. This is called the man-rightly U-test. That this is the test that SPSS picks for you in your comparison. Now, in the old days, without this procedure, when we do this kind of non-parametric test, we have to go to the statistics textbook or some kind of statistics manual, check the conditions, and from there, we know what test we need to do, and then we pick the test from the SPSS manual. But now you can skip all those steps because SPSS automatically picks the test for you. So this is the independent samples man-rightly U-test. Now, when you report your data, you have to tell which test you are using. So this is the name that you need to put into your report, or otherwise your readers do not know what you are doing here. The SIG is the significant value, so that is the p-value, and the p-value is 0.713. Now, ask you again, 0.713, so are they the same or not? Is the creative thinking the same or different across the gender? Yeah, they are the same. The reason is that p-value is so large that we go to the upper one. Okay, it is not smaller than 0.05. It means that if we reject the null hypothesis, the probability that we are wrong will be 71.3%. That is a very high probability, and we don't want to do that. Now, according to the tree here, we do not reject the null hypothesis, or otherwise, in other words, we say that the two genders are the same in creative thinking. But what is good about the non-parametric test procedure in SPSS is that you don't even have to think about that because it already tells you the decision. The decision is to retain. Retain means you do not reject. You do not reject the null hypothesis. So it already tells you everything. You don't even have to check the tree, the decision tree, because it already tells you the decision. So that's why many students, although the non-parametric test is quite complicated conceptually, many students like to use it in their data analysis because this procedure here is really convenient. But I would think that now, of course, in any case, if you can use the t-test, you can use the non-parametric test because the t-test requires more assumptions. The t-test requires that the data are scale level and normally distributed. If something can be done using the t-test, it must be able to be done in the non-parametric test as well. But I do not recommend using non-parametric test when you can use the t-test. The reason is that theoretically, non-parametric tests are more difficult to understand, although it is easier to do it in SPSS. Okay, remember that. We only use the non-parametric test when we cannot use the t-test and the ANOVA. Okay, but anyway, this is the conclusion for this case, and the conclusion is the same as our independent samples t-test before, right? We found that the male and female are the same in creative thinking, and now in the non-parametric test, we have the same conclusion. But what if we compare more than two groups? Again, we go to analyze non-parametric test, independent samples again. Now this time, we change the grouping variable from the gender to the grade. For the grade here, we have 3 possible groups. So in the settings here, again, we use automatic and run it. So this time, you look at the null hypothesis, the distribution of creative thinking is the same across grade. Now, again, this is the correct null hypothesis we want to do, but the test is different. Compare this. Previously, we had the man rightly used test, but now we have the independent samples Quasco-Wallace test. Again, this is picked automatically by SPSS because in this case, SPSS knows that there are more than 2 groups in your data. So this test is corresponding to the ANOVA in the case of normally distributed scale variables. Okay, but in this case, it is the non-parametric version of that. The p-value 0.000. Again, this is a small number, so you know you need to reject the null hypothesis. But you don't have to worry about that because it already tells you the decision. So it means that at least some of the grades are different in the creative thinking. That answer, that conclusion is the same as our ANOVA analysis before. But which group is different? Again, we need to know the post-hoc test result. Now, for this version of SPSS, we are version 25, you only have 1 table. If you are using version 26, you have more tables below that, and one of the tables will show you the post-hoc test result. But for this one, don't worry, we can still get the post-hoc test result, but you only need to double-click on the table here. You double-click on this table, and then you get another dialog with the conclusion on the left-hand side. On the right-hand side, you see the box plot. From here, you already know that grade 4 students seem to be different from the other grades. Now, down here, in the view option, there is one option called the pairwise comparison. This one is available when you have more than 2 groups. So I click on the pairwise comparison. You can ignore this chart here. Just look at the table. This is the post-hoc test in the non-parametric test. So again, we have pair by pair comparison here. Grade 5 and grade 6, p-value 0.066, which is larger than 0.05, so they are the same. Sorry, we have to look at the adjusted significance. This one, 0.198. This is greater than 0.05, so grade 5 and grade 6 are the same. 4 and 6, p-value very small. 4 and 5, p-value is also very small. So in both of these cases, we reject the null hypothesis. Or in other words, grade 4 is different from grade 5, and grade 4 is also different from grade 6. But 5 and 6 are the same. Now, this conclusion, again, is the same as what we got in ANOVA. But this time, we are doing it in the non-parametric test. Okay, so that is how you do non-parametric test and the post-hoc test. Now, again, when you report this, you have to tell the hypothesis and you have to tell what test you are using. Then you write down the p-value and write down the conclusion. And in this case, you also need to show the pairwise comparison results. Now, there is another type of non-parametric test, which is the related samples test. So the related sample test is like the pair sample t-test, except that it is a non-parametric version. But I will skip this one because it is quite straightforward. Now, finally, we come to the last test of today. That is the categorical data. Now, categorical data means that we have nominal or ordinal. As I told you last time, there is a good news and a bad news about categorical data. The bad news is that you do not have much choices. You do not have many choices in analyzing the categorical data. And the good news is that you do not have many choices in analyzing the categorical data, right? So for the inferential statistics, again, for categorical data, most of the time, we are using the chi-square test. The chi-square test. Now, the chi-square test, the hypotheses are written here. Null hypothesis, there is no association between the two variables. So sometimes you want to know if two categorical variables are related to each other. So you want to do the chi-square test. Like, so the null hypothesis is that there is no association between them. And the alternative hypothesis is that there is association between them. So it means that they are related to each other. One of them might affect the other one. Okay, sometimes you want to know if this is the case. So to do that, again, we go to analyze, but this time we cannot find it anywhere except this time we need to go back to the descriptive statistics. It doesn't seem a good choice, but anyway, the chi-square test is put inside the cross tabulation, and cross tabulation is a descriptive statistics. So that's why it is put inside here. Now go to cross tabs again. Okay, now, and then this time, let's compare two variables. I want to compare the gender and the grade as we have done last time. So I put one of them into the row and the other one into the column. Now, both of them are nominal data. So previously, we have already done the cross tabulation for this one. And here is the result from last time. So we know the number of people falling into each of the combinations. But this is not inferential statistics yet. This is just descriptive statistics. Now, to do the inferential statistics, we go back to the cross-tab dialog. And then we go to the statistics button here. Inside the first option is the chi-square test. So you just click it. You don't have to worry about how it is done. You just click it here. and we ignore everything else and go to continue and go to OK. So this time you get the same cross tabulation table, but you also have the chi-square test. Now, you have a number of rows in the chi-square test, but the only number that you need to look at is the Pearson chi-square, the first row, and then go to the right-hand side to look at the last number. That is the p-value. 0.623 is the p-value of your chi-square test. So let's look at the tree again. 0.623, that is a large number. Can you tell me which one should be taken? H0 or H1 in this case? P-value is 0.623. H0, right? Because you look at this tree again, just in case you are not already familiar with it. 0.623 is not smaller than 0.05. So we go to the upper branch, and the conclusion is do not reject H0. It means that we want to regard the H0 to be true. So the conclusion is that there is no association between the two variables. Now let's see if this is reasonable. Gender and grade. Supposedly, the gender should have nothing to do with the grade of the student, right? So these two variables should not be dependent on each other. So the conclusion here actually makes a lot of sense. Okay, there is no relationship between the grade and the gender. Now, but of course, in other cases, in your own questionnaires, might be the two variables are associated with each other. Now, in that case, you will get a smaller p-value, and then you can conclude that there is association between the two variables. Now, one more thing about the chi-square test. Down here, below the table, you see a remark. The remark is very important. So here it says that 0% have expected count less than 5. So what does it mean? It means that in this cross tabulation table here, now you see my frequencies in this table, all the numbers are quite large. And that is because I have a large sample size, 708. And the people are quite uniformly distributed across the different groups. Now, but in other cases, if you have a small sample or if most people are in one of the groups, then you might see that some of the frequencies here will be very small numbers. Now, in the chi-square test, SPSS actually needs to calculate something called the expected count in each of these boxes. And if you have small frequencies, then some of the expected counts will be small. Now, it turns out that if many of the cells have expected count less than 5, then the chi-square test will become invalid, and you should not believe in the conclusion here in this case. Now, I have written down this point in my notes here. The result will not be valid if many of the cells have expected frequency less than 5. And SPSS will warn you about that in the below the table, like this. But in this case, we have no problem here because we don't have any of such cells. But sometimes you might have some of the cells with expected count less than 5. Now, what is regarded as problematic? There is no unique answer to that, but many people think that if this number, this percentage is higher than 20%, this is a rule of thumb, okay? Many people use this. If this number is higher than 20%, then people will think that we have too many. And in that case, we should not rely on the chi-square test. So what do we do in that case? In that case, we want to combine some of the groups. Like suppose that we do not have many students in grade 6, and that might make the sum of the percentage, sum of the expected currents very small. Now in that case, I might want to combine grade 5 and grade 6 so that they become one group. When you combine them, the frequencies become larger, and then you avoid the problem of the small expected currents. So that is one way to do it. Another way to do it is to reduce your table until it becomes 2 by 2. Now, in 2 by 2, when you are having a 2 by 2 table, SPSS will show you another test result, which is called the Fisher's exact test. This one is not affected by the small expected current issue. And in that case, you can use this test in place of the chi-square test. Okay, that's it. So it means that you can always solve your problem. If you cannot solve the problem, then you combine your groups until you get a 2 by 2 table, and then you use the Fisher's exact test. So I have written down the criteria here, so you can always refer to it later when you work on your own data. So at this point, I have finished my demonstration. So if you look at our website again, here is what we have gone through. I have talked about these different types of tests, including one sample t-test, 2 sample independent t-test, 2 sample pair sample t-test, and also ANOVA. And then I also talk about chi-square test and the non-parametric test. And from the output, you see that sometimes SPSS is using the Mann-Riley U-test, and sometimes it is using Quasko-Wallis test. And also we need to do the post-hoc test for the non-parametric test as well. And finally, I have shown you how to do all these in SPSS. So at this point, you should already have some basic concept about how to do data analysis and conceptually and how to do it in SPSS. So you should be ready to go to analyze your own data. Now, next semester, I don't know if we have the chance to have the second class. And in the second class, we will be doing some kind of workshop where you analyze your data and I give you individual comments. But whether there will be such a class depends on the arrangement of the department. So let's wait for it and see if we can meet again in the next semester. Okay, so what test should I use if it is ordinal data? Ordinal data cannot be normally distributed. Normal distribution only refers to scale data. So ordinal data, you use non-parametric test. Okay, so at this point, I have finished this course. So I hope you find it useful. Finally, if you have not taken your attendance, please go to the website, go to the first page, and then take your attendance there. So I will also put up the video recording so that you can refer to it later when you need it. All right, so I think I should end the session here. Thank you very much for staying with me for the past few weeks, and I wish you good luck and success in your final year project. Okay, thank you very much. Okay, thank you.